All right, let's go ahead and start with practice exercise 85 today. Practice exercise number 85. So skipping over a few here, page 24. And want to approach this idea of inequalities, of absolute value, questions that you might see, for instance, next week on some standardized achievement tests. Questions that as you get to your senior year, you might see on College Board testing. Questions that if you try to actually solve it the traditional way, it's going to drive you nuts. But if you just think logically about it, makes life not too bad. Look at the first problem. Read that question for us if you would, Quentin, nice and loud.
How many integers, counting numbers, inverses of counting numbers, n0 satisfy 1 is less than the absolute of x minus 2/3, or is 1 greater than absolute x?
You were right the first time. 1 is less than. Hey, it's a good thing we're reviewing, right? 1 is less than the absolute value of x minus 2/3 is less than 3. And it gives us a little reminder there, those parallel bars mean absolute value. So a couple little things they reminded you of. First of all, what an integer is. It's a nice, easy number. And a second, that these parallel bars mean absolute value. So remember with absolute value, doesn't matter what's inside, positive or negative, it spits out positives, correct? It says how many integers could satisfy that inequality. Can you think of a value that if you plugged it in right there, it would work? Something if you subtracted 2/3 and took the absolute value, it would be between 1 and 3. Call it out.
Oh, 4, 6?
2 would work. If you took 2 minus 2/3, you get 1 1/3, right? What's the absolute value of 1 1/3, class? 1 1/3. Is 1 1/3 bigger than 1 but less than 3? So 2 would work. Is there another number you could plug in place of the x?
3.
Okay, because 3 minus 2/3 would be
2
2 1/3. Is 2 1/3 between 1 and 3? All right, so 2 would work, 3 would work.
3 1/3.
2 1/3.
Well, 3 1/3 would not be an integer. Right, it says integer, so we're only plugging in normal numbers.
2 1/3.
That's not a normal number.
Negative.
Nice, easy numbers.
-2.
That's everything.
It's not everything.
-2.
Negative, positive.
What about -1? What's -1, -2/3? -1 2/3, right? What's the absolute value of -1 2/3? 1 2/3. Is that between 1 and 3? So -1 could be plugged in. Is there another number?
-2.
-2, because what's -2 minus 2/3?
-2 2/3.
-2 2/3, but the absolute value of -2 2/3 is 2 2/3. Is that between 1 and 3? All right, so -2 could work. Any other numbers? No, because you plug in a -3, that's -3 2/3, absolute value is 3 2/3, that's not less than 3. You try to plug in a 4, well, that's 3 1/3 is not less than 3, right? You try to plug in a 0. 0 minus 2/3 is -2/3, absolute value is 2/3, but that's not bigger than 1. So there are 4 integers that satisfy. Do you see how to think through this type of problem? You're going to do the next 2 problems there at your seats, putting some thought into various integers that can work in those inequalities. Finishing exercise 85. All right. You busted. Now, let's go and take a look at these together. And Quentin was first done with these two problems. Quentin, how many integers satisfy 5 is less than or equal to x plus 3 is less than or equal to 10? 6. Which 6 integers?
2, 3, 4, 5, 6, 7.
Good. 2, 3, 4, 5, 6, and 7. 2 just satisfies being equal to the 5. 7 just satisfies being equal to the 10. Of course, everything in between is going to satisfy, so 2, 3, 4, 5, 6, 7 would satisfy. All right, Quentin, for the next one, how many integers satisfy 2 is less than or equal to the absolute value of x plus 1 is less than or equal to 5? Or more than 5. You were second. Did you get 6 for the last one?
Yes.
All right, what'd you get for this one?
8.
It is 8. Which integers?
1, 2, 3, 4. And then -3, -4, -5, -6.
Good. 1, 2, 3, and 4 all satisfy. Those are your positive integers, right? 1 just satisfies being equal to 2. 4 just satisfies being equal to 5. And of course, everything in between the 2 and the 3. But because of absolute value, we also have to count for negatives. Well, -3 would satisfy giving you a 2. And -6 would satisfy giving you the 5 when you take that absolute value. So end up with 8 integers. 1, 2, 3, 4, -3, -4, -5, -6. Questions on those, do they make sense now? Any questions? Anyone else get both answers correct? Just not as fast as Chris. All right, good. All right, which 5 did you have, by the way, Quentin, on the last one?
1, 2, 3, 4, -6.
So you got the 1, 2, 3, 4. You got all 4 positive integers. By the way, that's a clue. There's also going to be 4 negatives, right? And you got the -6. Just didn't think of the other ones. Were you the same boat, Ethan?
No, on the first one, I didn't have 7.
Oh, you forgot about 7. Okay, what about on the last one? You said you had.
I'm all right.
Oh, you got. Okay, I'm sorry. I thought you said you had 5 on the last one, like he did. No, okay. You had 5 of the 6 on the second one. All right. Questions at all on this? Any questions? All right. Let me go and collect those from you. Again, just kind of thinking it through, making sense of things, as opposed to necessarily solving an inequality the traditional way. I suppose it could be done that way, but I'm lazy and I like shortcuts. All right, if you would go and take out your notebooks, turn to the Theorems Corollaries section so that I can see that you got Theorems 63 and 64 copied down. We're also going to look at page 214 in your textbook. You did problems 11 and 12. So notebooks out so I can see the theorems are copied, and also have your textbooks open to page 214 and have out numbers 11 and 12, the homework that you did last night. So there's theorems 63 and 64. There's your theorems. There's 11. There's 12. Ethan is finding numbers 11 and 12, perhaps on the back side. Good. Let's see. Theorem 63 and 64. Good. And finding the other homework. I'll come back to you. There's the theorems. There's the 11 and 12, sort of. Maybe you did a lot of work in your head there. Maybe that's what it is. I'll come back to you. There's the theorems. There's the 11 and 12. I like the artwork there. Very nice. Good. I like the artwork you've got going on there, 11 and 12. And then the theorems 63 and 64. There's the theorems. There's the 11 and 12. There they are. Excellent. Let's go and take a look at this together. We're going to get to the theorems momentarily, so for now you can set the notebooks aside. We'll get back to those in a moment. Page 214 in your textbooks. Page 214, some of you needing to turn there. And let's see here. Chris, you're there. Would you read problem 11 for us?
A smokestack 75 feet high is held by 3 wires attached 10 feet from the top to the nearest hook. What is the length of each wire if each is fastened to the ground 40 feet from the stack?
All right, now there's a period and there's a comma. And so our punctuation needs just a little work there. A smokestack 75 feet high is held by 3 wires attached 10 feet from the top. End of sentence. To the nearest whole foot, comma, that was an introductory phrase, what is the length of each wire? So anyway, so how many of you have seen a cell phone antenna, a radio tower with the wires coming off of it? In fact, even a lot of telephone poles will have wires coming off of them to hold them in place. I've never seen this with a smokestack.
I don't know what that is.
A smokestack is a stack that has smoke that comes out of it.
I didn't know what it was either.
Smokestack, like right around the corner of that mill has that big tall smokestack, okay? I've never seen guy wires on a smokestack. But that's what we got. We got guy wires attached to the smokestack. If you look vertically at the smokestack, you know, as the smoke billows up in your face, which is what Santa Claus has to do if people are staying up late. We've got the wires coming off of this smokestack and attaching down to the ground, and they usually are at 120-degree angles to each other to provide stability. So the radio tower, the cell phone tower, or the smokestack doesn't fall down.
I don't like that
Again,
one.
I've never seen smokestack with guy wires. But anyway, that's what we've got. So we've got this smokestack. I'm going to redraw a smokestack. And it says the smokestack is how tall, Chris?
75 feet.
75 feet tall. And these guy wires are not attached to the top of the smokestack, but rather if you come down 10 feet, that's where the guy wire is attached. It's anchored there, and then it comes down and attaches into the ground. Of course, there's 3 of them. There's one on each side as we kind of go around. It's not that a round smokestack has sides, but there's 3 of them going around. We're just focused on, let's take one of these guy wires here, 10 feet from the top, attaches down to the ground. It says that they are attached, each of these wires is attached to the ground 40 feet away from the stack. Now, typically a smokestack is built so it gets slightly wider at the base and narrows as it goes up. It channels the smoke upward. It also provides stability. But for sake of illustration, let's imagine that the reason they needed guy wires is because they made this a perfectly vertical stack with no widening at the base at all. That's going to help the math work out just a little bit better here. So here's the picture. Smokestack, okay, 10 feet from the top, guy wire comes down, attaches 40 feet from the base. Question is, how long is the guy wire?
X.
Well, we can represent the guy wire, certainly X, but if the smokestack is built vertically, we can imagine a little right angle here, couldn't we? And if so, then class, we have formed with this guy wire, smokestack, and ground, a little right
Triangle.
Actually, it's a great big right triangle, I did. A great big right triangle, where we know that one
Like,
leg of the right triangle is 40 feet. The guy wire is our hypotenuse, but we're not told the other leg. But we kind of know the other leg, don't we? 65 feet. After all, the tower is 75 feet, and the guy wire is 10 feet from the top, so that'd be 65 feet from the ground. So we now know 2 sides of a right triangle, and we're trying to find the 3rd side. What should we do, class? Pythagorean Theorem. If you didn't do that, each calculator's at the ready. Hypotenuse squared equals leg squared plus leg squared. Now I can do 40 squared in my head. 65 squared, not as strong on that one. 3225? 4225. All right. We can add those together. That'd be what, 5825? I'm going to go on a hunch and say it doesn't come out evenly. In fact, I know it doesn't because at the very beginning of the last sentence it said to the nearest whole foot, meaning we're going to round our answer. Go ahead and hit the square root button. It's going to be a decimal. I don't care because I'm going to round it off anyway. What do we actually get when we take the square root? 76.3 dot dot dot. All right, when we round to the nearest whole foot, that comes to 76 feet. So approximately 76 foot long guy wires. How many have that answer? You thought it through, you set up the right triangle. All right, does it make sense now? How to set that up?
I did not.
Does it make sense
I guess
now?
we have to do proportions. Yeah,
No, not a proportion, because I know 2 sides of a right triangle and ask for the 3rd side, so Pythagorean Theorem. Let's look at number 12 and read that for us if you would. Let's see, Ethan.
At a certain hour of the day, a flagpole casts a shadow at 20 feet at the same time that a 10-foot pole casts a shadow of 6 feet. Found the height of the flagpole.
All right, so here's the idea. Now, if the sun is high in the sky, high noon, right, then there's no shadow, correct? It's just directly above the flagpole. But as the sun begins to set in the sky, as it were, if there's flagpole, there we go, Audrey, not to be outdone by her great artwork. As the sun sets, there's a rather lengthy shadow that would be formed by the angle of the sun, correct? Well, let's suppose we've got that flagpole, but nearby, again, the sun is really infinite distance up there, but we've got another flagpole that's, shall we say, a 10-foot tall flagpole, right? And it says that the 10-foot flagpole casts a 6-foot shadow. So then in that case, the other flagpole that it tells us casts a 20-foot shadow must have some height of unknown length, correct? Question for you. The sun's going to hit both of these at the same angle, which means this angle is the same in both triangles. And assuming the flagpole is straight up and down, which is typically how a flagpole is installed, we also have a right angle in each triangle, which means each triangle has to be similar to the other, because we have angle, angle, or one acute angle in the right triangle. And if triangles are similar, corresponding sides of similar triangles are proportional. So that the ratio of any two sides, which we call the ratio of similitude, holds true. So I don't know the comparison of these two sides. It's a ratio of x to 10, right? But I know that the ratio of these two sides has to be the same as the ratio of these two sides, 20 to 6. And by using the corresponding sides proportional, we have a proportion. Solve it at your seats if you didn't set it up this way last night. So again, basing this off of the idea of similar triangles, proportional sides, let's find that missing side. Does it say to the nearest whole foot? No, it just says find the height. So we're going to end up probably getting a fractional answer here.
Yeah. It's 33.3 repeating.
33 and a third?
33. I don't know what I did, but I got 6 in this times square root of 2 feet. Because I don't know how I got this, but I had 18 instead of 20.
Even though it said 20?
Yeah, I don't know how I got 18.
All right, do you see what you should have done?
Well, yeah.
All right, did anyone have 33 and a third feet? Okay, a couple of you did it, good. Questions from those who did not?
I did that portions of
Does it make sense why it had to be set up this way? All
I
right.
set it up that way. I had just the numbers wrong.
All right. Questions? All right, again, just getting you to think, how do we apply Pythagorean Theorem outside the realm of geometry class? Well, there's one way. How do we apply similar triangles outside the realm of something else? For instance, you're standing outside and you notice that, let's suppose you are really long neck, I know.
Ethan.
No.
This is Ethan.
No, it's not.
So we're going to say Ethan is, let's see, you're 6'2", 6'3"?
6 foot 2.5.
Let's round. Let's say your shoes 6'3". Thank you. You are 75 inches tall. And let's suppose you go outside and you're like, hey, my shadow is, hold on, measure that for me, Mom, 25 inches. And then you notice there's a big tree. And the tree's shadow is, I don't know,
600.
38 feet.
600.
And the question is, how tall is the tree? Well, again, the same sun hitting you is the same sun hitting the tree nearby. The angle's going to be the same. The triangles then would be similar. So, well, let's cancel the inches here. You would say, one way to look at this is comparing the two sides to each other, 3 times your shadow.
Yeah, it's a ratio of 3 to 1.
3 to 1 body to shadow has to also be a ratio of 3 to 1 tree to shadow. How tall is the tree at your seats?
114.
114 feet tall.
Even start.
Not as smart, apparently.
No
So
wonder.
again, you can use this. I mean, no, you're not going to climb the tree with a tape measure. You don't have to. Use math, similar triangles.
Don't give me
Anyway,
that.
that's free. Turn in your notebooks to the proofs of theorems corollary section. The proofs of theorems and corollary section. Last night you copied theorems 63 and 64. Want to go ahead and discuss the proofs, or to do the proofs of those two theorems, and also show mathematically how we'll work with these two theorems. Theorem 63, if you'll put that at the top of a new sheet of paper. there in your notebooks. The theorem that you copied last night said this: if two chords intersect within a circle, then the product of the segments of one is equal to the product of the segments of the other. For what we're going to condense this down to is to say this: for intersecting chords, products of segments are equal. For intersecting chords, products of segments are equal. Kind of reduce the entire theorem down to that. If you would, down below where you write Theorem 63 for intersecting chords, products of segments are equal, go ahead and draw a circle or something that is somewhat circular. If you're OCD, you can use a compass. If you're lazy like me, you don't. Let's go ahead and name our circle Circle O. And draw any two chords so that they intersect. Pick one chord, let's call it AB. And then for the next chord, don't make it look perpendicular. Try to make it look like a different length. So I'm going to go, kind of close to the center. I'm going to go further from the center here. And I'm going to take, so this is clearly a smaller chord. It's not perpendicular. There's nothing special about it. I'm going to call this CD. I'm going to call the point of intersection P. The theorem again says, if two chords intersect within a circle, that's what we have, AB and CD intersecting at P, then the product of the segments of one equals the product of the segments of the other. So we're given, of course, a circle, Circle O, with chords AB and CD intersecting at P. So that's the given. We have intersecting chords, and if chords intersect, prove that the product of the segments of one chord is AB, but its segments are AP and BP. Prove that the product of those segments, prove that AP times BP is equal to the product of the segments of the other. Well, the other chord, CD, has two segments, CP and DP. We're going to prove that the product of AP and BP equals the product of CP and DP. Now, of course, the segments themselves are not equal. No way. AP is probably bigger than all of CD put together, but the product of the segments has to be equal. That's what we're going to prove. Once you have that down, two columns, statements, reasons. Go and get down your first statement and your first reason. The lazy math teacher in me, look, just despises writing out the word intersecting. Like, there's got to be a quicker way to say that. But INT is used for interior, not intersecting.
If you just write INT, SEC, then might as well just write intersecting.
Yeah, I mean, by the time you write another, yeah, whatever. There just isn't a shorthand
Why don't you
for it,
write
unfortunately.
like ITS?
That means it's. Like, its chords, its diameter, its perimeter, its radius.
Why don't you just draw like, I don't know, a line like this and then draw a line, but it's not a multiplication sign, it's just like a line that shows intersection.
We'll just roll with it. All right, so let's think about what I'm given here. Not much.
Squat.
Yeah. Okay, so let's look at what we're trying to prove. Synthetic method came up totally empty. Let's look at the analytic method. I'm trying to prove that these two things multiplied equal those two things multiplied. Now, we've seen this a couple times before. Thoughts?
Why don't we make a proportion?
Make a proportion. Because if the product of two quantities equals the product of two other quantities, either pair of values may be used as the means and the other as the extremes in a proportion. So let's see, how might I set up a proportion here? Jamie, you said proportion about the same time. Kristen, what proportion are you thinking?
would be like AP is to CP as BP is to DP.
AP is to CP as BP is to DP?
No, flip that. The DP is to BP.
As DP is to BP? Like that? Alright. Does that work, class?
Yeah, it
Yeah.
does.
These are the extremes. Those are the means. That was the key. They had to stay together, means, extremes. It could have been reversed, that's fine, but that works, right? Okay, so continue on the analytic method. Jamie said if we can get this proportion, we can get this statement by just cross-multiplying, right? But how could I get proportional pieces? How do I obtain proportional pieces? Somebody else?
Like not me.
Well, not Jamie.
Multiplication. Or no, get triangles.
Triangles.
Similar
triangles,
triangles.
right? What's the number one way of getting lines proportional? Get similar triangles class and use CSSTP. Okay, so we can get this statement if two triangles are similar to each other. Now, which two triangles, Chris?
ADP.
ADP, let's see. ADP. I just want to draw an auxiliary line.
Is that the only one you can do though?
And what would be the other one?
Well, it'd be CBP.
CBP, this little guy up here. So we make a little line here and a little line there. That seem doable? Okay. So we want ADP and CBP is what you said. Is that correct? That's what he said?
Yes.
Okay. How do I get triangles? Well, first of all, I have to get the triangle. So number two, let's make some auxiliary lines here. Here we go, Chris. You got this.
No, I'm on PTSD. Draw 80 and CB.
Reason?
2 points determine straight line.
Right, we do have 2 points. The last time we drew an auxiliary line, it was because only one perpendicular would be drawn, but we're really just joining 2 points. So 2 points determine a straight line. And go ahead and draw that auxiliary line. Now I will say this, if you had alternated the CP and DP, they still would have stayed together, right? And then you would have had ACP, you would have drawn this auxiliary line, and BD would have had that one. It doesn't really matter, right? Either these two triangles on the sides or the ones we drew, no problem with the ones we've got. They work good. What?
We already have one angle.
All right, so we said we wanted to get triangles similar, someone besides Chris and Jamie. How do I get triangles similar? Okay, you said AA, Ethan. Angle, I need some angles equal. Okay, Ethan, you got any angles for us?
The vertical angles of P.
Okay, so if I named the angle, let me move my P right here so it's out of the way. If I call this angle 1 and angle 2, you're saying we can say that,
They're equal.
right, angle 1 equals angle 2 because?
All vertical angles are vertical.
We can say all vertical angles are equal. I'm just lazy and don't like to write the word all if I don't have to. Vertical angles are equal. I think that's actually the wording though of the when two straight lines intersect, the vertical angles formed are equal, something like that. Anyway, vertical angles are equal. So we got some equal angles here. But you said AA, angle, so that's only one pair of angles. We need some more. Now, Kendall, I think I heard your voice as well, saying angle, angle. Are there some other angles we could try to get equal? Audrey, Genesis. Did you help me? I don't think you helped me yet, Quentin. Y'all looking, help her out. Need some more angles, thoughts?
Angle B and angle D.
All right, you're saying angle B and angle D. What are your thoughts on B and D? How would we get them equal?
Angles in a circle.
Okay, angle B is an inscribed angle, that's true. D is an inscribed angle. What do we know about inscribed angles?
Equal to its arc.
Ooh.
Half the time.
Equals half its arc, right? So literally, what does angle B equal?
Half of arc AC.
Half of arc AC. Does everyone see that? This angle B has to equal half of arc AC. What about angle D?
F of arc AC.
Is also inscribed and also is going to intersect half of, or equal half of AC. So number 4, Quentin, if we go ahead and state that, well,
Or angle B equals F of arc AC.
and also state that
Angle D equals F of arc AC.
because right. State that angle B equals half of arc AC. State that angle D equals half of AC because an inscribed angle equals half its arc. And then because angle B and angle D both equal halves of equals, or really you could say they equal the exact same thing, number 5, back to Kendall, we can say that
Angle B equals angle D.
because of a couple ways we could phrase it.
They're equal to the same thing.
Right, quantities
Equal
to same quantity
are
Could
equal.
you
are equal.
Could
You-
you say it has a equals or equal?
You could say halves of equals are equal. You could just say substitution. That would work as well. Any of those 3. Substitutions usually are go-to, but hey, it gives axiom 1 a chance to be used. We don't use that one very much. So there's a pair of angles, 1 and 2. There's a pair of angles, B and D.
The same word.
So if I've got angle, I've got
Same word.
similar triangles. So Genesis number 6, I should state that.
Triangle ADP is similar triangle CDP.
Right, A and C do correspond as the angles we didn't mention yet. D and B do correspond, and P and P do correspond. So yes, ADP is similar to CBP by, and once we have the triangles similar, Audrey, okay, so, right, AC is to CP as DP is to BP by CSSDP, corresponding sides of similar triangles are proportional. And if that proportion is true, then I can say that AP times BP equals CP times DP because anyone?
CSSDP? No, substitution.
Product of the means equals product of the extremes. And there we go. Questions on that proof? Questions on that proof? Theorem 64. All right, turn to class notes where you have your pictures and proportions page. Turn to class notes where you have your pictures and proportions page. Now, technically, this is not a proportion, but it is based off of a proportion, so we're going to include it anyway. Go and draw yourself a circle. We don't actually even care what the center is named. We just want 2 chords. For sake of ease and lack of creativity, let's call these A, B, and C, D, and let's again have them intersect at point P. For these intersecting chords, anytime you see intersecting chords, you know that product of segments equals product of segments. That is that AP times BP equals CP times DP. We'll get that down on that pictures and proportions page. The product of these 2 pieces equals the product of these 2 pieces. Then go and get out some scratch paper, some loose paper we don't really care about necessarily. And let's do some practice with this fact, that the product of the segments equals the product of the segments. Or you could say the product of the segments through a point is constant. I believe that's one of the corollaries. We don't ever really use that statement in and of itself, but it's the truth. Pick any point in a circle, draw any chords you want. The product of the segments must be constant because the product of the segments would always equal any other product of segments. Let's suppose I know that segment AP is 4.5 inches. Let's suppose I know that segment BP is 4 inches. Let's suppose I know that segment CP is 3 inches, and I want to know the length of segment DP. Well, typically what we'll want to do is label directly on the picture, like we do with all our other things. Here's 4.5, here's 4, here's 3, here's X. And then, very simply, we take the product of the segments, set it equal to the product of the segments. I like to start with whichever chord has the X in it. What's the product of the segments, class? 3X. Has to equal, what's the product of the segments? 18. Again, calculator can be useful, especially when dealing with fractions. And now we solve, and you can do this in your head. What is the length of segment DP?
6 inches.
6 inches. Pretty easy. Taking product equals product. How about this? Same picture, different given information. Let's suppose we know that CP is 2 centimeters.
How did you get 18?
4.5 times 4 equals 18. Just as 3 times X equals 3X. Okay? All right, let's suppose we know that CP is 2 centimeters, AP is 5 centimeters, BP is 4 centimeters, and I want to know the length of the entire chord CD. Again, label on the picture what you got. CP, that's 2. AP, 5. BP, 4. And it says I want CD, which is this whole thing. But does the whole thing factor into the problem? No. What does factor is the other segment. So again, let's just call the other segment X. What equation should I write now? Genesis?
2x equals 20.
Right, so obviously the X equals 10. However, keep in mind, you didn't want DP, which is 10 centimeters, you wanted all of CD, which is 12 centimeters. You just add the extra pieces in there. So obviously one chord is a length of 12. How long is this chord? 9. It's 9 centimeters. The product of the segments is 20, but the actual length is 9. Make sense? What if we saw something like this? That AP is to BP as 3 is to 2. CP is 3. CD is 11. I want to know how big are both AP and BP. I'm going to go and redraw the picture. At your seats. Label the pieces and parts on your picture. And if you need to redraw as I do, that's fine. So we had a chord AB. We had a chord CD. Intersected P. AP is to BP as 3 is to 2. Quentin, thoughts? That is actually a way of looking at it. I would say AP is 3x and BP is 2x, right? Anytime things are given in ratio, stick the x's on them. So 3x, 2x. CP is 3. But BD, or PD is not 11. The whole thing is 11. Thoughts, anyone? 8 for the other piece. So, what equation do I write, Kendall?
5x.
Ooh, careful. Product of segments, 3x times 2x equals 3 times 8.
6x equals.
Ooh. That algebra, 6x squared. It's been a little while since you had to multiply x's, right? But 3x times 2 is 6x squared is equal to 24. Go ahead and solve it out here, Kendall. Divide away the 6 to get
4.
X squared is 4. So what's x? Technically positive negative 2, but we're talking about a length, right? So class, just positive 2. All right? So,
6 and 4.
6 and 4. 6 for AP, 4 for BP. No units given, no units needed in the answer. Questions on how to use this picture from Theorem 63. Again, it's not a proportion, but it was based on a proportion.
Can we do another one of those?
We will tomorrow. I need to move ahead now, though, to Theorem 64. Theorem 64. And for this one, we had 2 lines drawn to the same circle. One a secant line, one a tangent line coming from the same external point. Now, if we were asking about the angle formed, we would say it's equal to half the difference of the intercepted arcs. Go ahead, Theorem 64, the top of a new sheet of paper. Theorem 64, there in the proofs section. And go ahead and write this down if you would. Secant is to tangent as tangent is to external segment. That's the proportion we're going to prove based on this. I believe the wording was if a secant and tangent are drawn to a circle from a common external point, then the tangent is the mean proportional between the secant and its external segment. But translating that into a proportion, secant is to tangent is to external segment. Go and draw a circle. We don't even have to necessarily name it, but call the tangent PT. And let's call the secant PS. And let's go and just name this point here G. G doesn't get used very much. We're given PT, tangent at T, secant PGS. PT tangent at T and secant PGS, with G and S being the 2 points of intersection. What proportion are we trying to prove? Say it with me, class. Secant is to tangent as tangent is to external segment. Again, secant is to tangent as tangent is to external segment. What is the secant here? Well, the entire secant would be PS, correct? So PS, secant, is to tangent PT as tangent PT is to the external segment of the secant PG. Make sense on the lettering? Tell you what, we don't have time to prove it in this lesson. We'll go ahead and finish the proof tomorrow. But for now, go ahead and set up your 2 columns, statements, reasons. Go and get down your first statement, first reason, and we'll go ahead and finish this in our next lesson. There is no homework this evening, so I'm going to go and end the video here, but you have another minute or so to finish getting the proof set up.